Welcome to the first unit in the lecture on Bayesian probability theory. My name is Wolfgang von der Linden, and I will enable you to help Captain Bayes and her crew to solve their adventures in probability theory. The first episode helps us to enter the discussion of Bayesian probability theory. And the aim of this unit is to provide you with the language to describe probabilistic problems, have a first glimpse on the different concepts of probability theory, and to enable you to solve elementary problems. Let us start with some definitions that will help us to find a language to formulate problems and solutions. Problems with uncertain outcome can also be formulated as questions. For example, the question may concern a random experiment, as for instance the random compass. A possible question could be, in which direction will the compass needle point? Another famous experiment is performed with a die, where we can ask the question, how many pips will the die show at the next throw? But the question does not necessarily have to do with random events, like what's for lunch tomorrow? The uncertainty may just be due to lack of information. It doesn't even have to have anything to do with future events whose outcome is uncertain for everyone. For instance, where is Captain Bayes? At least Captain Bayes herself will know the answer. All these problems have one aspect in common. The answer is uncertain for whatever reason. Each question has a well-defined set of results which we call outcomes. Like the 4 compass directions, north, east, west and south, or the number of pips on the die, or the possible dishes for lunch like roast or potatoes, or the whereabouts of Captain Bayes, like in the ship's galley, on deck, and so on. We call the total set of possible outcomes the sample space, and we denote it by capital omega. A question can be associated with a random variable that assigns a real unique number to each outcome. This is especially useful for measurable results, like the number of pips on a die or the weight of a fish. For the directions of the random compass, we can assign an angle. For a question that favors one particular result, one can use 1 for the result itself and 0 for all remaining outcomes. Random variables can be discrete or continuous. Discrete variables have distinct values, which in many cases are natural numbers, like the pips of the die. The sample space omega of a discrete variable is countable. We will focus on discrete variables throughout the first 7 units. Continuous variables, on the other hand, have uncountably many values, as for example a real number in a certain interval, or the weight of a fish, or the angle of a direction, or the time when something happens. Continuous variables are in some aspects special. Counting of all possible or favorable outcomes is not possible, and a different principle of measuring, measure theory, has to be used. Interesting phenomena like scale invariance or the Bertrand paradox will await us at the end of this course when continuous variables will be discussed. Now we continue with the formulation of probabilistic questions and generalize the result of a random experiment, which so far was called outcome. We want to ask not only the question, will the die show 5 pips, but also questions like, will the die show an odd number of pips, which includes the 3 outcomes 1, 3 and 5. The generalized result of a random experiment is now formed by a subset of the sample space, which we call an event. Note that we use curly brackets, the set brackets, to indicate a set of elements. There is no order in a set of outcomes, in contrast to later discussed tuples of outcomes, where the order is important. Let us analyze how many events can be formed by the subsets of the sample space. To this end, we take a look at the event space denoted by sigma, which is the space of all possible subsets of the sample space omega. We call this also the power set of omega. The smallest event containing no outcome is called the empty set and is never realized. It is therefore also called the impossible outcome. Events containing only one outcome are called elementary events. The event that covers the entire sample space is the certain event or the one element. As for the complexity of the questions, there are no restrictions. We could also consider multiple dice or repeated throws of a single die. Or we could even combine a die experiment with the random compass. I leave it up to you to think about the corresponding sample space and the elements of the sigma space. In addition to outcome and event, another term plays a crucial role in probability theory: the proposition. A proposition is a statement that can either be true or false, nothing in between. Like, the coin will land heads up, or Caesar was a Roman. Propositions are particularly obvious in binary experiments. These are experiments with only two outcomes. Such an experiment is called Bernoulli trial. One of the most famous examples is tossing a coin, which has the two outcomes heads and tails. Every event A can be rephrased as a proposition by stating the experiment will have event A as its result. This proposition can be true or false. The opposite of proposition B can be addressed using the negation operator, not B. We will discuss propositions and their usage in Bayesian probability theory in more detail in Unit 3. Now that we have defined the objects of the probabilistic reasoning, it's time to introduce the notion of probability. The aim is to assign a number to each event that quantifies its partial truth. The larger the number, the more likely the event will occur. There are some basic assumptions concerning this number called axioms of Kolmogorov. The first assumption states that each event is mapped to a real number between 0 and 1. 0 indicates an impossible event, one that can never happen. A probability 1, on the other hand, marks a certain event that will definitely happen, thus called the 1 event. The 0 event, empty set, will always be mapped to probability 0. It should be noted that there can be more events that have a 0 probability. The 1 event is the set of all possible outcomes, or rather the entire sample space, and it has the probability 1. An example for a certain event is the die will show any number of pips, anything between 1 and 6. To be able to work with probabilities, we need the rules of probability theory. There are two basic rules in probability theory which can be explained most easily by set algebra. Since events are sets, we will use Venn diagrams to illustrate them. A set or subset is depicted by ellipses. Since each event is a subset of the sample space omega, it can be drawn as an ellipse inside omega. The first rule of probability theory concerns the logical OR of two events, A and B, say, which corresponds to the union of two subsets. The probability for A or B is treated in the sum rule. To begin with, we consider exclusive events A and B which have no overlap. For those, the sum rule states that the probability for A or B is the sum of the individual probabilities. It is particularly obvious if we identify the probabilities with the area of the ellipses. In that case, the union of the two sets is equal to the sum of both areas. A special case applies to the complement of the set A or the corresponding event, and can be depicted as the area inside omega that is not A. In this case, the sample space omega contains both A and not A. Remember that we have defined the probability of the sample space omega to be equal to 1. Therefore, we get for the probability of the complement of an event 1 minus the probability of that event. For non-exclusive events, there might be an overlap which corresponds to the intersection of two sets. If we sum the probabilities for the events A and B, we count the elements contained in the intersection of the sets A and B twice. Therefore, we have to subtract the probability for the event A and B. That brings us to the generally valid form of the sum rule. The second rule of probability theory, the so-called product rule, tells us how to work with events that are combined by the logical end, like the term that we subtracted in the sum rule. A detailed discussion of the product rule follows in Unit 3. There are now some questions for you to train these concepts. There is also an alternative way to express probabilities, which is called odds. Odds map events not to the interval 0 to 1, but to any positive number, and they are commonly used in sport bets and some applications of statistics. The odds of an event A can be directly calculated from its probability by the ratio of P for A divided by the probability for its negation, P for not A. Odds represent the chance that an event will occur compared to the chances that the opposite will happen. For example, the odds of 2 to 3 for an event states that on average you can expect 2 times the desired event and 3 times its negation, which corresponds to a probability of 2 divided by 5 or 0.4. In many cases, a colon is used to distinguish odds from probabilities. Note, however, that the sum rule and the product rule do not apply to odds. Nevertheless, odds will become useful in a later chapter when we discuss Bayesian update rules of knowledge. Now that we have learned Kolmogorov's axioms and the rules of how to work with probabilities, the next question is how to assign probabilities, how to get the numbers. There are actually 3 ways to do so. First, we will discuss the classical approach, which works in the case when elementary events are assumed to be equally probable. Although it seems like a circular argument, there are many examples where it works very successfully. The other 2 alternative approaches will be discussed in future units, and I will introduce them here just as an outlook. There is the frequentist approach, which is based on statistics and defines probabilities as relative frequencies of measured data. This is also sometimes called orthodox statistics. The Bayesian approach is the main focus of this course. Here, probability has a very general meaning. For the assignment of probabilities, we will discuss the principle of transformation groups to deal with continuous variables to assign probabilities for events if nothing is known apart from their definition. You will also learn the principle of maximum entropy. That allows you to assign probabilities based on additional knowledge. In this context, we will rediscover some results of the classical approach as special cases. Now let's see how our friends Bernoulli and Laplace solved probabilistic problems in the classical way. Well, they formulated the principle of insufficient reason, also known as the principle of indifference, which states the following. If the elementary events, the outcomes of an experiment, can be regarded as equal in the sense that none of them is preferred in any way, then we can assign the same probability to all of them. This is often true in the case of symmetric objects like a die or a disk, as we have seen in the random compass. And it can also be due to missing information. For a perfectly symmetric die with 6 outcomes, this leads to an equal probability for each of the 6 outcomes of 1/6, or which is approximately 17%. For the coin, the probability for each side is 1/2. Next, we want to generalize these ideas to general events. For the case of equally probable elementary events, the classical definition of probabilities of general events is given by the ratio of the number of favorable outcomes to the number of possible outcomes. This follows readily from the sum rule of exclusive events. Let's consider the die again as an example. For the event of an odd number of pips on a die, there are 3 outcomes that make the event true. The number 1, 3, and 5. The total number of outcomes is 6, so the probability of the event of having an odd number of pips on a die is 3 divided by 6, which is 1/2. Here we could also argue with the principle of indifference. 3 sides show an even number of pips and 3 sides an odd number. There is no way we can distinguish these 2 sets of sides. Therefore, odds and even number of pips should have the same probability, 1/2. The question of the probability of having a day off on Captain Bayes' ship is more tricky. First, one has to identify the full sample space omega. Since the compass needle is twisted twice, one has to combine each result of the first dial with all 4 possible results of the second dial, resulting in a total of 16 possible outcomes. Now, the order of directions is important. North-west is a different outcome than west-north. In contrast to the curly brackets for sets, we now use round brackets for these tuples to indicate that the sequence is important. In the second step, we need to identify the favorable outcomes for the free-day event, namely north-south, south-north, east-west, and west-east. Hence, there are 4 favorable outcomes. The probability for the free-day event is thus given by 4 divided by 16, which is equal to 25%. This concludes the first unit. Please have a look at the bonus material, feel free to ask questions in our forum, and be encouraged to test your knowledge in the quiz.